All right, basic differentiation rules. So what we're going to do today is we're going to talk about how we can find derivatives without having to do all of those tedious limits. So talk about a couple rules here. These are just, um, basic things that you can observe if you do enough limit definition derivatives. Take a function that's a constant. Well, obviously, if you have a function, something like f of x is equal to c, then the slope of the tangent line at every point is always just going to be 0. So we don't need to work out a limit to know that the derivative there is 0. Let me just say, just in case we're clear here, if I define f of x to be equal to c, then I can say df dx, also known as f prime, is equal to 0. This d dx notation is like an action to take the derivative. So d dx of the function 5, that's like saying what is the derivative of 5? It is 0. Now, if you've done enough limit definition of the derivatives on power functions, you'll recognize the power rule. So the derivative of x raised to a power is nx to the n minus 1. So up to this point, quite a few times, we've taken the derivative of things like x squared, and you probably recognize that we get 2x every time we do that. Take the derivative of x cubed, you're going to get 3x squared. Take the derivative of x to the 10th, you're going to get 10x to the 9th. So instead of working out all those limits to figure that out, that's just a shortcut rule that always works. Number 3, the constant multiple rule. So if I have a constant, let's say I have 5 multiplied by x cubed, if I want the derivative of that, that is exactly the same as multiplying 5 times the derivative of x cubed. I know the derivative of x cubed is 3x squared, thus the resulting derivative is 15x squared. So if it was just x cubed, we'd bring the power down, make it a 2, which is what you see here. But because the 5 is there, the 3 and the 5 just end up multiplying together. So you have to make sure you see the difference here. The derivative of just a constant is 0. But the derivative of a constant times a function is not 0. It is the constant times the derivative of the function. And then the last one here is the sum and difference rule. This simply states that if you take the derivative of the sum of terms, say x squared plus x cubed, you can do that by simply taking the derivative of each term separately. 2x plus 3x squared. So if you have a sum or a difference, just take the derivative of each term separately. Notice that there is no, at this point, product quotient rule. And that is because products and quotients do not work so easily. So the derivative of the product of two functions does not equal the product of the derivatives. We're going to talk more in depth about that later. So this only works with sums and differences. It doesn't work with products and quotients. So number 1 here, let's use the definition of the derivative to show that essentially that the derivative of 5 is in fact equal to 0. So verify graphically. We've already done that. We'll do that now. I'll do that first. So here is the function y equals 5. Obviously, if you choose any 2 points along here and you find the slope of the line passing through them, you're going to get 0 because the average rate of change is 0 and the instantaneous rate of change is 0 everywhere. So y prime is equal to 0 because the slope or the slope of the tangent line or the instantaneous rate of change is always going to be 0. Now let's actually prove it using the definition of the derivative. Y prime is the limit as h approaches 0 of f of x plus h minus f of x all over h. In this case, that is the limit as h approaches 0 of. Now, f of x is just 5, but so is f of x plus h, because here's x plus h. It doesn't matter what x value you're at, you're always at a height of 5. So this is the limit as h approaches 0 of 0 over h. Now, this is different than something that approaches 0 over something that approaches 0. I don't know what this is. Which would be indeterminate. What we have here is something that is 0. So if you have 0 divided by something that's approaching 0, well, that's still just 0. So this whole thing is really just equal to 0. So what we've, geez. So what I've shown here is that the derivative of this function is equal to 0. All right, and then let's go through the tedious process of proving the power rule specifically for x to the fourth. So I'm going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. So this right here is the limit definition of the derivative of x to the fourth. Now I'm going to use that binomial theorem to expand x plus h to the fourth. X to the fourth, well, let me make sure I have my Pascal's triangle right here. 1, 4, 6, 4, 1. Okay, x to the fourth, 4x cubed, 4x cubed h, 6x squared h squared, 4x h cubed h to the fourth minus x to the fourth all over h. X to the fourths are going to cancel out. I'm going to factor a common h out of the numerator. So I'll have h times 4x cubed, 6x squared h, 4x h squared h cubed all over h. H's cancel out. Substitute in 0 for the remaining h's, and everything here is going to go to 0 except for the first term, which is 4x cubed. Therefore, the derivative with respect to x of x to the fourth is 4x cubed. So, not a generic proof of the power rule, but a specific one that shows the rule is true. It's a lot easier to just bring the 4 down and make it a 3 as opposed to going through that process every time. All right, so let's find a couple derivatives using the rules. This is simply a power function. So I can find this derivative by just bringing the exponent down and subtracting 1 from the previous exponent. So my f prime here will be 3/2 x to the 1/2. Just that simple. Now, using the rules up here, specifically 2 and 3, I want to be able to write all of my functions in the form of ax to the n in order to use those rules. So this one was already in that form. This one is not, so we're going to do a little bit of rewriting here. This is the same as 1 over 2 x to the 2/3. So the cube root is equivalent to a 1/3 power. And then I'm going to take this term and move it up top and just change the power of the exponent. So my original function here is the same as this. And now I have it in that form that I can apply the power rule to it. So I'm going to bring the negative 2/3 down. And then subtract 1 from that exponent. So my derivative is going to be negative 1/3 x to the negative 5/3. And then I'm going to take my negative exponent, move it back down into the denominator, and express it in positive exponent form. So when you're giving these answers, I would like you, if you have negative exponents in your answer, to rewrite them as positive. And all you have to do is take the term and move it to the denominator or to the numerator. Move it up or down, that will change it. Now, you don't have to go back into radical form, but just in case you wanted to, this is also the same as -1 over x to the 5/3 is the cube root of x to the 5th. So that would also be a valid answer. So when you see something like this, the first thing you're going to want to do is rewrite it in this form and then take the derivative. All right, now, as I mentioned up here, we don't have a quotient rule for derivatives. I can't just do the derivative of the top and the bottom. It does not work that way. So we have to do some rewriting. So what I'm going to do on this one is I'm just going to split it up. This function h is exactly the same as x cubed over x squared plus 2x squared over x squared plus 5x over x squared plus 3 over x squared. And then continuing my rewriting, this is x plus 2 plus 5 over x plus 3 over x squared. And then once again, just like over here, I'm going to rewrite these last two terms so they look, again, more like that ax to the n idea. So one more rewrite, x plus 2 plus 5x to the -1 plus 3x to the -2. Now I can finally take that derivative. All right, the derivative of x is 1. The derivative of 2 is 0. The derivative of 5x to the -1 is -5x to the -2. Bring the -1 down, subtract 1 from it. And then minus 6x to the -3. Once again, bring the -2 down, subtract 1 from it. So let's write this in simplest form. 1 minus 5 over x squared minus 6 over x cubed.